Hello. So now we'll do the moment of inertia for a linear object, and the first linear object we will pick as a rod. So in this lecture we will calculate the moment of inertia of a rod for which the mass is m and the length of the rod is given L. Okay. And as we know, when we calculate the moment of inertia, the axis is a very big aspect. So to calculate the moment of inertia in this case, I am assuming my axis to be perpendicular to the rod. This is perpendicular. And this is passing through the center of mass of the rod. Okay, so we'll calculate the moment of inertia of the rod about the axis which is perpendicular to the rod and passing through center of mass of the rod. So now you can see in this case it's a combination of many points. This linear object is a combination of many points which are assembled along this line. And we have a formula to calculate moment of inertia for point masses. So here we have to cut the elements, and those elements should look like the point. So what we will do here, from the axis and perpendicular to the axis, we will move till a distance x. So we move to a distance x and we make a cut. Okay, this is the cut we made after moving to distance x with respect to the axis. I'm calling this axis, this point as O. And after moving x, we further moved by a distance dx. So this is your dx distance, and we make one more cut. So between these two cuts, we will be having a point element to be more precise, and mass of that point element I'm taking as dm. Okay. So for this point element, we know the moment of inertia of this point element with respect to my axis. So let's first calculate the mass dm. So this rod is a linear object. So in this case, we will define the linear density. So linear density, which is defined as lambda, for this rod will be equals to m by L. While defining this, I have assumed this linear density to be uniform. Obviously, if this linear density is not uniform, if it is given the equation, this density is not uniform, in that case, whatever is that density, variable density, we will take it there. Okay. In this case, I am assuming it to be uniform. So since we get the linear density, now we can calculate the mass dm. The dm mass can be defined as the linear density multiplied with the length of the element, which is defined as dx. Okay. So lambda is a constant. If it is a variable, we'll put that variable value here. So dm will be equals to m dx upon L. This is my equation 1. So we have calculated the mass of our element. Okay. Now for this element, we will define the moment of inertia with respect to our axis. So moment of inertia for the element with respect to axis is defined as DIO. It's a small value because see, we are calculating the moment of inertia for the element. So we cannot take it completely I naught. So it is di naught. That value will be equals to, the formula is ml square. If you remember, moment of inertia due to a point mass is equals to mr square. Moment of inertia for a point mass due to the point mass I is equals to mr square. This is the formula for moment of inertia for a point mass. This is moment of inertia for point mass. This is the formula, where m is the mass of that point and r is the distance of that point with respect to axis. So here my element is a point. Mass of that point is dm and the distance of that point with respect to axis is x. If I use the same formula here, the moment of inertia for my element with respect to the axis will be equals to dm, which is the mass, multiplied with x square, which is the distance of the element with respect to axis. In this case it was r, here we have taken it as x. So let's put the values. It will become m by L x square dx. This is DIO. This is equation 2. So this is the moment of inertia for my element. Okay. Since I can recreate this whole object with the use of multiple elements. These are points. So if I add moment of inertia of all the points existing onto this rod, I'll be getting the moment of inertia for this rod. Only thing we have to keep in mind is that whenever we are calculating the moment of inertia of the element, axis has to be same, because if you remember, moment of inertia can be added, it can be subtracted. Condition is they have to have the same axis. So each and every element will be having the same axis. So I can write the moment of inertia for whole body I will be equals to integration of DIO, meaning I'll be adding all the moment of inertias from minus L by 2 to L by 2. This is the meaning. If the x value will be changing from minus L by 2 to L by 2, we will be covering the whole object. Okay, so let's put the values. So it will be m by L. I'm taking m by L outside. X square dx, because this is constant, that's why I'm taking an outside, because it does not depend upon x. Since we have to integrate for the whole body, so we'll have to put the limits. The limits will be put from minus L by 2 to L by 2. If we change the limit from minus L by 2 to L by 2, we will be covering the whole body once. So let's integrate. So integration of x square is x cube by 3. Limits from minus L by 2 to plus L by 2, and we will put the limits now. Let's take 3 out because it's a numerical value. We can take it out. So x cube, in place of x cube, we'll put L by 2 cube minus of minus L by 2 lower limit power cube. So it becomes m by 3L. This value will be L cube by 8 minus, and 1 minus will come from this because you see minus to the power, whenever we have minus 1 to the power odd powers of minus 1, the minus remains there. For even power, minus becomes positive. Here we are having the odd powers, so minus will remain there. So minus will come outside. There is already one more minus here, so it will become positive. So L cube by 8. So it will be m by 3L multiplied with L cube by 4. 1 by 8 plus 1 by 8 will be 1 by 4. So that whole value, if you see, it will be ml square by 12. So moment of inertia for this rod about the axis which is perpendicular to the rod and passing through the center of mass will be equals to ml square upon 12. This becomes the formula. This formula one can memorize, but you have to see this is only the moment. It's not like this is the moment of inertia for all the rods. This is the moment of inertia for rod about axis which is perpendicular to rod and passing through center of mass of the rod. So only about this axis, this will be the moment of inertia. Okay. So one more time, let's summarize that. We wanted to calculate the moment of inertia for a linear object, and the linear object we have picked as rod. So, and we wanted to calculate the moment of inertia about the axis which is perpendicular to the rod and passing through center of mass. So to do that, till now we know the moment of inertia for point elements. So what we did, we cut an element which was the point element. We calculated the mass. Of that point element, assuming this density to be uniform. After calculating the mass of the element, we applied this formula and we calculated the moment of inertia of that element about the given axis. This was this. And after calculating the moment of inertia of the point mass about the given axis, we integrated that because we need to calculate the moment of inertia for the whole object, keeping in mind that axis has to be same for each and every element. So this is the same formula we'll be using. So after doing the calculation and putting the values, upper limit and lower limit, this is the result we got. In this result, the formula comes out to be ml square by 12. Here we have to remember the mass of the rod is m and length of the rod is L here. Okay. So whenever we are having a rod of mass m and length L, and if we have to calculate the moment of inertia for that rod about the axis passing through center of mass and perpendicular to the rod, this is going to be the formula. Okay. Thank you.